Le Chatelier's principle states that an equilibrium system that is subjected to any stressor will tend to shift to a new equilibrium state in attempting to offset that stressor. Previously, we talked about Le Chatelier's principle with regard to concentrations of substances in an equilibrium system and the effect of a catalyst. Now, we're going to deal with Le Chatelier's principle as it pertains to changes in pressure or volume for gaseous equilibrium systems. The key to figuring out how a change in pressure or volume will affect a gaseous equilibrium system is to look at the balanced equation and determine the number of moles of gas on each side of the equation. Let's give an example. Here we have an equilibrium system. Suppose we increase the pressure on this system. If we increase the pressure, we know that a gaseous system will tend to get smaller. If we personify the system, we can say, if we increase the pressure, the system wants to get smaller. Now, if we look at the moles of gas on the left side of the equation, there are 2 moles of gas on the left for every 1 mole of gas on the right. Which way will the system shift to get smaller? And that would be to the right. On the other hand, if we decrease the pressure, think of a gaseous system that's under a certain amount of pressure. If we let up on that pressure, the system will tend to increase in volume. So in this case, if we decrease the pressure on this system, the system, we can say, wants to get bigger. Which way will the equilibrium shift in order to get bigger, in order to take up more space? Well, it's going to shift to the left because 2 moles of gas certainly take up more space than 1 mole of gas. How about for this case? H2 plus I2 yields 2 HI. The number of moles of gas on the left are 2. 1 plus 1 is 2. And on the right, it's also 2. So, pressure changes on that equilibrium system result in, no shift, because there's no advantage to shifting one way or the other because the number of moles of gas on each side is the same. With regard to shifts, more specifically, if the partial pressures are affected, then there will be shifting, otherwise there won't be. Now, if that doesn't make any sense to you, let's try to explain. Let's say we have this equilibrium system, and we inject a bunch of neon into the system. That is, Ni. So we're going to put neon in. Ni, Ni, Ni. Put more neon. Ni, Ni. Like the Knights of Ni. The partial pressures of the 3 gases that are involved in the reaction are unchanged. Remember that the partial pressure is the pressure that a gas would exert if it were by itself in the container. And if we inject something into this vessel that doesn't react, then it's not going to increase or decrease the amount of any particular reactant or product, and therefore the partial pressure of those reactants and products is not going to change. No shift. And finally, whenever we change the volume of a gas, can change its temperature often. That's more of a topic related to physics and thermodynamics, but let's just say that as long as the temperature doesn't change, the value of the equilibrium constant is also unchanged, no matter what we do with pressure and volume. Now, if the temperature changes with volume changes, then K is affected. But, barring that, the value of K is not affected by pressure-volume changes. Let's summarize. Just like changes with concentration, changes in the pressure or volume of a gaseous system at equilibrium produce compensatory effects in the system. For increases in pressure or decreases in volume, we can think of the system as wanting to get smaller. The shift is toward the reaction side having the smaller sum of gaseous coefficients. For decreases in pressure, or increases in volume, the system wants to get larger. The shift is toward the reaction side with the larger sum of gaseous coefficients. We see now why, in the production of NH3, ammonia, via the Haber process, the reaction is carried out at a high pressure. And the Haber process is shown there at the bottom. We're wanting to produce NH3. And so we want to increase the pressure, because if we increase the pressure, the system wants to get smaller. We have 2 moles of gas on the product side, and on the reactant side we have 3 plus 1 is 4. So if we're trying to produce NH3, we certainly want to exert as high a pressure as we can so as to continually push that equilibrium towards the product side.